thanks everyone for tuning in, and I'm happy to see so many people excited about the new book and excited about using Python for data analysis and data science and other related applications. So I just wanted to talk to you a little bit about the book and why I wrote it and what it's about. And then most of the screencast, I'm going to dip into a couple of examples, fun examples that I use in the book to illustrate some of the tools, and then I'll of course answer all of your questions as we toward the end of the screencast. So, why did I write the book? I guess, as many of you are probably aware, Python has become one of the most popular languages for interactive data analysis, building data-driven systems for web analytics on the server side, and also for people doing research. If you look at surveys, Python, along with the R statistical programming language, is one of the most popular languages that people use for data science. However, I saw that maybe a year ago or over the last couple of years that the learning resources for people doing data analysis really weren't as good as they could be. There are a number of really excellent Python books, Python language books. Many of them are published by O'Reilly and many other publishers. But if you wanted to learn about data analysis topics, scientific computing, how to use NumPy, SciPy, Matplotlib, you want to pull in some data in tabular format, maybe apply some operations to it, do some data aggregation, make some plots. It really wasn't very easy for people to get started. I had a number of people come to me and say, I have a lot of experience using Excel, and I would like to start using Python. Where do I start? And found that I was sending people to 4 or 5 different documentation websites for various open source projects. And it was a little bit, daunting for people to get started using Python. So I wanted to create a really practical introduction for new users so they could get up to speed learning the parts of the Python language that they need to work with data. So it's not only the additional libraries which are specific to data analysis and scientific computing, but also a biased introduction to the Python language, sort of ignoring a lot of the sort of system development and object-oriented programming things that are often the focus of Python books, and really focus on the tools that have specifically to do with working with data. But I also wanted the book to be something that would be very helpful to people who already have a lot of Python experience, who can just skip over the sort of introductory Python material and are just looking to learn some new tools and become more proficient at using the cutting-edge developments for working with data in Python. So how did I get involved with this? So I started out as a mathematician back in my college days, and I went into the financial industry after I graduated, and it's there that I started using Python for working with data. I also was an R user as well, and I saw a lot of things that I liked in R, and I wanted to build those things in Python. So I've been developing open source Python libraries, in particular the pandas project, really since the beginning of 2008. I've been working very actively to make Python a better language for data analysis and data science. And I speak at conferences and it's been sort of making the rounds, sort of spreading the good news about all of the awesome libraries that people have been building. So the book is very much it's a book of tools. There are other books which are more focused on data analysis methods using open source tools. O'Reilly has a book, Data Analysis Using Open Source Tools. This is really a book about Python and the Python tools that you need to work with data. I guess I call it the key steps in the data life cycle. How can you read data, get data into the right form from many different sources? What are the things that you need to know to kind of whip the data into shape? That often data comes in, it's very messy, requires quite a bit of munging to regularize, and fix problems with the data. Often the way that data is stored in databases and files is not the way that you need it to actually do your analysis. You need to do some reshaping or transformation of the data, moving the data around in particular ways. You might need to take a very large data set and apply some transformation or aggregation to create a summary that you want to use to build, let's say, a pivot table or some kind of visualization to present that data to somebody else. There's quite a bit about visualization and presentation, and I will show you some of that in the screencast, the kind of tools that we're talking about. So the main tools in the book that the book focuses on are the ones on this page. So the first, presented at the very beginning of the book, is the IPython project, which is not a tool for data analysis, but it's the environment for executing code, exploring the results of that code, doing some software development and debugging. So if you're building a process that is processing a huge amount of data and it's slow and you'd like to figure out why, I take you through how to profile your code and understand where the time is being spent in the code. So doing profiling and timing. If there are problems, bugs that you're trying to figure out, like how to use the interactive debugger. So IPython's a really amazing project that's grown a lot in the last 2 or 3 years, and I will show you a little bit of IPython in the live demo. Now, NumPy is the array library for Python, so many of you may already have experience with NumPy, but it provides the multidimensional array object and matrices. So if you're familiar with R and MATLAB, it provides the sort of array processing functionality that you're familiar with from other languages. Most of the book is about pandas, which is another open source project that I've been the main developer on for several years. So it's the high level toolkit for data analysis. It sits right on top of NumPy and gives you high level data manipulation tools for loading in tables of data, and gives you sort of easy to use and convenient APIs for sort of slicing and dicing, aggregating, transforming, kind of all of the things that you need in your tool belt to get the data into the form that you need. And the last major library that's discussed in the book is matplotlib, which is the main plotting library in Python for creating most widely used plotting library for creating two-dimensional plots. So just a little bit about how the book's organized. So there's a couple of introductory chapters where many people won't have Python installed. They won't have all of the requisite libraries for following along with the rest of the book. That's in the first chapter. After that, there is a chapter full of a few fun examples, a couple of which I'm going to show you in a few minutes, just to give you an idea of the kinds of things that you'll see in the book. And then the next chapters I listed here. I guess what I call the modern scientific computing environment in Python. So the IPython a shell and code exploration environment, the NumPy library for working with arrays and applying batch operations on arrays of data, and plotting with matplotlib. Now, most of the rest of the book is focused on pandas. Because the book is about data analysis, and pandas is really whole goal in life is to make you more efficient working with data. The introduction, I guess there's an introductory chapter to teach you about the pandas data model, working with labeled arrays. It's kind of the key concepts of data alignment and sort of how to work with the data once it's been loaded into Python. There's a lot of tools talking about how to get data in and out of Python from many different sources. You might have data in CSV files or tab-delimited files. You might have JSON data that came from the web. There's just a lot of things to learn there with the nuts and bolts of how to get that data loaded into the right object so you can proceed with doing the actual analysis. And the remaining chapters are focused on specific topics in pandas, so the data wrangling, sort of data munging problems of rearranging data into the right forms, applying operations to clean up and regularize the data. Chapter 9 is focused on data aggregation and group operations. So if you're familiar with SQL, you've probably written a group by statement in your life, so you can do do all of those things right within Python. If you have a sort of a table of data, you can group the data by one or more keys and apply operations to those groups, which might be sort of crunching it down to a summary form or doing some other form of group transformation or fitting a model to the groups of data. The last couple of chapters that I listed here are a little more domain-specific. Pandas happens to be a really excellent library for time series analysis. So Chapter 10 focuses on working with time series data, which could be really small time series or really large sort of high-frequency time series that you want to be able to sort of crunch down and sort of work with in a nice way. So, and the book will be out later this month. I'm told it will be available in time for Strata, and I will be speaking at Strata New York in a couple of weeks. So I'm very excited to have the book in print. It's been available in ebook form for a number of months while I was writing it, and it's been pushing out early release updates to readers. So I'm so very excited to see the book completed, and I think it will be very helpful for people who are learning Python and sort of want to have. And even for really experienced users who want to have that reference book on the shelf to be able to look up various topics. So I'm going to switch over right now to share my screen. All right. So hopefully everyone can see my screen. So what I'm going to show you here is walk through a fun example that I like to use in demos, and it's in the second chapter of the book. It's exploring some baby name data from the U.S. Social Security Administration. So if you go to the Social Security Administration, there's a site there where you can download historical data on the popularity of every name given to new births in the U.S. So I think it goes all the way back to 1880. So it's fun to analyze how naming trends have changed over time, and names that have become popular at various points in time and then stop becoming popular. Some of them relate to people who were famous at a point in time, or biblical names, which have been more or less popular as time has gone by. So I'll walk you through kind of the tools that we're looking at and do some fun things with this data. And the environment that I'm exploring the data in is a tool called the IPython Notebook. So it's part of the IPython project. I will show you that website. If you use Python, you should definitely check out IPython. It's grown a huge amount in the last few years, and I think it's played a really pivotal role in making Python programmers more productive. One of the tools that's in it is a web application that here I'm connected to it through Safari. It's running locally on my machine, and the idea is that you have editable code cells where you can execute arbitrary Python code. Here I've just imported a couple of the most important Python libraries that are used in the book: NumPy, Pandas, and Matplotlib. I've set a couple of options just for the demo, and then at the end I put just the simple statement, print hello world. And if I press Shift Enter, what it's done is sent that code to a running Python process, executed it, and captured the output. So if I had instead put a plot inside this code cell, suppose I generated some normally distributed random data, take the cumulative sum, and then plotted it, what it gets back is a plot that is captured and then inserted into the browser. And what's nice about this format is you can save this document. You can think of it as a living, computational document in the style of Mathematica and some other projects. But you can save this document and share it with people, and it contains your code and output and plots. So it's a nice way to sort of explore data and create and share analysis. So in the case of this baby names data, so once you download the archive of all of the data from the Social Security Administration, you get a directory that's full of files that look like this. So their year of birth and then the year, and the thing that you get back is on the next line here, I just opened the file from 1880, and read all of the lines into a Python list, and I'm just printing out each line in the first 10 lines in the file. And so you can see that every line here contains a name followed by a sex, and then the number of babies that were given that name, I guess, here in the year 1880. So you can see that the fields are delimited by commas. So the easiest way, and there's no header, so here we just have to infer that the header, the column names for this table would be name followed by sex followed by births or number of births. So we can read this data into a table in Python using the pandas read CSV function. I pass the path to the file along with a list of the column names that I want to give to the columns of data. So the thing that I get back is the pandas data frame object. So if you've ever used R, you're probably familiar with data frames. A data frame is it's just a name for a spreadsheet. It's a rectangle of data. It has a number of columns. The columns can have names. You can also have labels for the rows. You see here I've called the data frame's head method, which prints the first 5 rows of the data frame, and the row labels are just the numbers 0 through 4, and you can see the column names, name, sex, and births. And I can select columns from the data frame by using the notation names 1880 subname. I just pass the string here, and that selects the name column from the data frame. So you can see these are all of the names. You can see there's my name, Wes, at the end of the file. I guess they were still naming people Wes even back in 1880. So that's one of the most important objects that I work with in the book. That's found in pandas. So one of the key facilities in data frame that's used to analyze data is group by. So I don't have time to explain in gory detail what's going on here, but if I take this data frame and I want to apply some operation to, say, aggregate the births data by sex, what I can do is say names 1880, group by sex, select the births column, that's what this .births does, and then do .sum, which is going to aggregate up the number of births by sex. And now the thing that I get back is this is also a pandas object, so you can find out what kind of object it is and by using the type method in Python. So the series object that I get back here is very similar to a data frame, but it's one-dimensional. So it's just an array of data, and the labels here, F and M, are the unique sex values in the data frame. And so the index has been named sex. So that's so a series can represent a column in a data frame or just a one-dimensional labeled array of data, and you can see the associated metadata here. That I selected the births column, so the result that you get back has name, births, and the index here of sex knows that it arose from the sex column in the data frame. So you have all of the information you need here to understand this aggregated result. So what I'm going to do in the next code block is I've got data files from 1880 up through 2010. So I'll generate that range of years using the Python range function. And for each year, I'm just going to use Python string interpolation here to create the file path to that file, and then use the read CSV function to read in that data frame. So you probably noticed here that the year is not contained in this file, so I want to be able to identify which year each row belongs to. So I insert into that data frame a year column, which just has the constant value of the year for that data file. So for the 1880 data set, if I did names 1880 sub year equals 1880, execute that, then you can see that I now have a year column in the data frame that's 1880 for the whole data set. And the reason that I'm doing that is because I'm taking each chunk of data for each year, and then I'm appending that to a Python list. So I'm going to run all this code here. I just had to print out some status so you can see the progress it's parsing each file. Okay, and it's done. And so the pieces list that I assembled here now contains, each element is a data frame. So you can see that the first element at position 0 are the births from 1880. And if I do pieces sub -1, that's going to be the last data frame in the list, which are the names from the year 2010. And so what I'd like to do is to assemble all of this data into a single data frame that I can then start to slice and dice. So a function I can use to do that is pandas concat. I pass the list of chunks of data. I don't care about their index. You see all of their each of these data frames has a row index, which goes from 0 through n-1, which is the length of the data frame. So there are many cases where the row index of the data frame is meaningful, and when you concatenate the pieces together, you want to keep track of that. In this case, I actually don't care about it, so that's why I passed this special ignore index equals true option. So the result that I get back is a much larger data frame that now has about 1.7 million rows. And this is the main data set that I'm going to use for the rest of the example. So if we look at the first 5 rows of the data frame, you can see that the data at the beginning is from 1880, as we would hope, and the data at the end, so the tail of the data frame, is from 2010. So one thing we can do is we can get a count of the total number of births observed in the data set for each year and each sex. So one way that we can do this is using the data frame's pivot table function. So if you've ever created a pivot table in Excel, you're probably familiar with pivot tables. The idea is that we're aggregating one of the columns, so in this case the births column, and then we have one or more fields that we want to group the data on. So here we're grouping on year and sex, but we want to lay out unique years on the rows of the resulting table, and on the columns we want the unique sex values, and we want to aggregate using the sum function. So I'll run this code, and the thing that we get back, so we get back a large data frame here, and you can see that the result is what you would expect. We have a data frame that is now on the rows. It's labeled by year, 1880 through 2010, and in the columns we have the unique sex values. So if we just wanted the total births for total number of baby boys born in each year, if I select the M column from the data frame, I get back a series that's indexed by year. And you can see that it has 131 values, and its name is M. So one thing we can do with this data frame is plot it to get just to see the number of births over time. So taking that data frame, if I call its plot method, I want to give a title to the resulting plot, and I pass that into the plot method. And the plot that is shown is a time series plot over the history. So you can see the sort of rise of births at the end of the 1910s. We have wartime here, and then the baby boom, baby births drop off, and then you can see sort of a steady increase up through 2010. So having these. So if you've done a lot of Python, haven't done much pandas, one of the nice things about pandas is that it integrates together all these tools, in particular sort of array operations with NumPy, which is the underlying array library being used here, and then visualization tools like matplotlib. So if you wanted to create this plot by hand, you would need to write quite a bit of code utilizing the matplotlib library. So it's nice to be able to create nice looking plots with minimal effort. So let's see here. So I'm going to do a couple more complicated things with the plot. I just wanted to show kind of some interesting trends with baby naming over time. So the first thing is that you notice that the number of birds has increased over time as the population has gone up in the U.S. So it'd be nice to be able to have for each name and each year to know the fraction of babies that were given, say, the name John or the name Philip. So what we can do is, and you also want to compute that fraction within sex. So there are some names which are given to both boys and girls. So what we can do is write a little Python function, this add prop function, which takes the birds column and then normalizes by the total number of birds within each group. So this is some fairly advanced group by stuff with pandas. So don't worry too much about the mechanics here. But what I do is I write this function which adds this new prop column, which is the proportion of birds for each name. I group the data by sex and year and apply that add prop function, which then creates a new data frame that now has this new prop column. So if I look at the tail of the data frame, you can see that some of these names that are very unusual. Let's look at the last 50 rows of the data frame. So there's a lot of very unusual names that start with Z, and the proportion of birds, it looks like the data set cuts off all names which were given to fewer than five babies. So each of the ones that had 5 birds, you can see that the proportion for that year is very, very small. You can, of course, verify that the proportion sums to 1 for each year and sex combination. So if we group by year and sex, select the proportion and sum that up, that we can see that the total proportion for each year and sex combination is 1. So another operation I want to do is to select the 1,000 most popular names from each year and sex combination. So, I guess early in the data set, I will show you that there were many fewer names given to. I guess there was a smaller universe of names given to babies, and that's changed over time. But I just want to select the most popular 1,000 names for each year and sex. So what I can do here is write a little function, get top 1,000. I take each group of data, sort by birds in descending order, and then I take the first 1,000 rows. That might be a lot to process, but you can trust me that it does the right thing. So I group the data by year and sex, apply the top 1,000 function, and then here's just a little tweak. I'm resetting the index of the data frame, which we could get rid of it, but I'm going to leave it here. So now you can see that the size of the data set has gone down significantly in size because I selected out 1,000 observations from each year and sex combination, and there's 131 years, so the total size of the resulting data frame is about a little less than 262,000, which is pretty much what we would want. There are some cases where you might want to separate the data into the boy data and the girls data, and you could do that like this. Suppose you just wanted the top 1,000 names for boys, so you could select that data by first doing this Boolean operation, comparing the sex column to the string M, and then if you pass that into the data frame square brackets indexing, you select out that subset of the data, and the same for the girls. So if we take this top 1,000 data set, again, as earlier in the example, let's aggregate by, instead of by year and sex, by year and name. So we get the total number of birds for each name and for each year. And so you can see that the columns in the resulting data frame is now very long. Each column represents a distinct name. So if we wanted to see all of the total number of boys given the name Wes, which is my name, we can see that during the 50s and 60s there were quite a number of people whose official name was Wes. If you change that to Wesley, you can see that there's a lot more traditional folks giving them. My name is actually, well, my middle name is Wesley. You can see a lot more boys and girls, I assume, were named Wesley over the course of the data set. So if we wanted to see the trend in a certain number of, I guess the trend in the number of births for a certain number of names, we could select, say, the names John, Harry, Mary, and Marilyn by passing that list of names to the data frame that selects a subset of the data. And then I can create a plot where each of these four names is plotted on a different plot. So I use the data frame plot function again. So subplots equals true makes a different plot for each name. So you can see that for those four names that we selected here, that you can see the trend over time. And it's interesting that the number of births by year has consistently gone down for all of those names. So there's something going on here. It could just be that people aren't naming their children Harry or Marilyn anymore. But there's a bit more to it than that. So one thing that I did here to try to understand, well, do people just not like these names anymore, or maybe people are just getting more creative about the names that they're giving. So one thing that you can do to try to understand this is to take the top 1,000 names, and now instead of looking at the number of births by name, I'm going to sum up the proportion of the total that was given. The proportion of the total that's found within the top 1,000 names. So here I sum the proportion column, compute a pivot table, group by year and sex, and sum up the results, and then plot it. And so you can see what's happened here. I changed the limits of the plot to 0 to 1.2. Let me make it go from 0.7 to 1.2. And so if you look at the plot here, you can see on the y-axis goes from 0.7 to 1.2, is that the percentage of babies that are represented among the top 1,000 most popular names has been decreasing steadily since the 1950s. So one thing you could conclude from this is that the number of different names that people are giving their kids has been increasing steadily, so that the naming diversity has increased substantially. So we can actually verify this in a little bit more systematic way by looking at. So one way that I looked at this data and I said, okay, what's one way that we could further quantify the change in naming diversity? So see here that I computed the total proportion that are represented in the top 1,000 names, but suppose that we wanted to see how many of the top 1,000 does it take to get to 50%? So, so how many names does it take to represent 50% of the population born in each year? So a way that you could do that, and now I'm just going to select the boy data for the year 2010. Now, if we sort by the proportion in descending order and then take the cumulative sum of the proportion, let me show you what this looks like. We get a cumulative sum of the highest proportions in the data set, and then we can search in that cumulative sum of proportions to compute where the proportion reaches 0.5. So if your brain hasn't completely melted thinking about this, basically what this means is that if you take the 116 most popular boy names in the year 2010, that represents 50% of the boys born, so only 116 names. But that's changed significantly over time, so if you look at the year 1900 instead of 2010 and do the exact same thing, then you can see that in the year 1900 that it only took 24 names to represent half of the boys born. So you could infer from this that that people have gotten a lot more creative about naming their kids for one reason or another. So you could do this a bit more systematically. So I took this operation here of finding the number that the number of names that it takes to get to halfway, and we can pack that up into a little function. So I call it get quantile count, and you can even specify the quantile that you're after. So here it's 0.5, so halfway between 0 and 1. I then group by year and sex, take this group's data and apply the get quantile count function, and that gives me back and then I'm rearranging it. So the result, let me show you what this looks like here so you can see what I'm doing. So the thing that I get back is a pandas series, which is indexed by year and sex. So it's just an array of data where you can have each aggregate. And then I call the unstack function, which is a data rearrangement function, a pivot function, which rotates the sex field into the column so that I have one column per sex in the table here. So then I can take this data and make a plot. And so you can see that sometime, I guess, after 1980, the diversity in naming in the top 50% of baby names just exploded. So it went from slightly over 50 for female babies to well over close to 250 in 2010. So it's kind of an interesting and fun trend in the data. So another thing that's very interesting is looking at, and I have to give much credit to Mr. Hadley Wickham, who many of you are probably familiar with. He looked at the distribution of the last letter of names in each year and how that trend has changed over time. So that's something that we can do here with these tools pretty easily. So if I take the names data and select the name column, I have a special string operator in this object where I can select the last letter of every string in the data set. So that gives me kind of a new series where I have the last letters. So I do that here. I select the last letters. I tell the last letters object that its name is last letters. And then I want to aggregate the names data. So along the rows, I want the last letters. And in the columns, I want to aggregate by sex and year. And then I'm just going to select out the years 1910, 1960, and 2010 to just make the data a little easier to understand. We're just looking at snapshots over the course of 50 years. And so the table that I get back is now, again, a data frame, and in the columns you can see the columns are sex and year. So this is an example of a hierarchical index in pandas. So I can select out just the female aggregated data or the male aggregated data in a pretty simple way. But you can look at the whole aggregated data set in this form, and on the rows you can see the total number is indexed by the last letter of the name, and you can see the total number of births in each year for each sex and last letter combination. So the last thing to sort of make the final plot is we want to take this data and normalize it by the total number of births for each year. So I can take that guy, total births, and if I sum it up, that computes the total number within each sex-year combination. And then I can normalize the table by dividing by the sum. I have to cast a float because I'm working with integers, and you can get some integer truncation issues if you're using Python 2.7. And the resulting data frame is now a table of proportions instead of total numbers of births. And the reason that I'm creating this is I now want to make a plot. So I'm going to create an array of subplots, and then I plot the male data on the top subplot and the female data on the bottom subplot. And so the punchline of all this, we get back a plot, and really the most important thing to see here is that if you look at, what have I done here? So if you look at the male data, the most striking thing about this data is that the number of names ending in D has plummeted in the 2000s, and the distribution of last names ending in N has exploded. So you see nearly 35% of boy names given in 2010 ended in N. There's some other trends in the female in the girl names, but they're sort of less striking than this sort of increase in, I guess you could call it the sort of N revolution in boy names. So I don't know the reasons for this, but I think it's a fun trend. So you'll remember it next time you talk to one of your friends whose name ends in N, or if your name ends in N. So that's a fun example, just to kind of show you a little bit about the tools that I'm looking at in the book. So the focus is on things like group operations and nuts and bolts of how if you didn't know how to do any of the stuff that I showed you, how you would start with a table of data that you loaded from one or more CSV files that look like this, and then how to compute derived statistics and do group operations and slice and dice and aggregate the data, and then end up with and be able to sort of create intuitive visualizations. So there's a lot of things that you have to learn here to be able to use these tools. There's nuts and bolts with selecting the data, filtering down to the portion of the data set that you want, how you would do. Here I did actually some pretty complicated things like grouping the data by year and sex and adding a derived column containing the proportion of names for that group. So these are things which can be quite complicated to do, but once you understand how the tools work, it's all kind of built from the same set of building blocks. And of course, all of this is built on top of the venerable NumPy library, which is what we have to thank for scientific computing. In Python, it's really the thing that has made all of these things possible, is having that sort of foundation of sort of matrix and array logic in Python, very fast array logic. So you can actually get at the underlying NumPy arrays held inside these objects, but there's quite a lot of data which is stored here to kind of represent this fairly complicated data set. So I'm going to switch over to answer some questions that might have accumulated. Okay, so I see, so one question here I see, so what improvements does pandas provide over conventional Python for raw data parsing? So for example, a JSON file containing raw text data, and make such raw data more presentable. So pandas has a number of high-level tools for processing, let's say, JSON data into this tabular format. So if you were, I don't have any examples prepared, but suppose you had a large sort of data set coming from the web. It's sort of an array of JSON objects, or a large JSON object that you want to extract some data from. So there are a number of tools in pandas for extracting that data from the JSON object. Once you've loaded the JSON object using one of the many JSON libraries for Python, you can pull the data out of that JSON into a data very easily. And one of the benefits of using the pandas data frame for working with that data is that all of the operations one is that all of the operations have been highly optimized, so they're geared toward working with very large data sets. As you see here, I was working with a table of 1.7 million rows, and it's very snappy, and all of the sort of slicing and dicing and crunching down the data is very fast. The other thing is that doing multi-dimensional data analysis, or grouping by 2 or 3 or 4 fields, and applying operations to multidimensional data, and then having a convenient way to work with that data once you've sort of done the processing. So the indexing functionality, which is built into the pandas data frame and series objects, makes it really easy to work with multidimensional data. Whereas if you were just doing pure Python, you'd have to be sort of you'd have to do a lot of the work yourself of moving data around between many different dictionaries and keying the data off sort of complex keys, tuples of three or four elements. But if you wanted to then rearrange that data, it would be quite a bit more cumbersome, in my experience. So another question that I see here is how good is the performance and speed of Python coupled with pandas on a given data set as compared to R or any other data analysis tool? So the performance is very favorable compared with R and other data analysis tools that I've used. Particularly with things like group operations, the most often comparison with R is with Hadley-Wickham's Plier library. The performance is very, very good. So if you're using, if you're doing a kind of a standard kind of aggregation, things like mean and standard deviation and count and kind of basic summary statistics, those operations are all highly optimized and will be actually quite a lot faster in Python with pandas than they will be typically in R. I think in most other sort of data reshaping, data rearranging types of operations, you're going to have very comparable performances and performance in some cases a lot better. Things like merging and joining data sets, I didn't really have time to show much sort of merging and joining of data sets, but the merging is very, very fast. So sometimes people come up to me and say, yeah, I did this merge with these two 5 million row data frames, and it was almost instantaneous, and and whereas doing it in R sometimes you'll have to wait sort of 10 or 15 seconds for a merge to go through. So we've worked very hard to make the tools easy to use and high performance, which is not always so easy to accomplish. Let's see. So how would you best split up the plot command if you were doing a particularly complicated plot? So there are a number of plotting conveniences that are found in pandas, but let me go back to the demo here. So you can see that in this case, I made a plot, and I didn't do anything too complicated with it. What have I done here? I don't know what kind of bug I have found here. Let's try this out. Pardon me. So in this case, I made a plot of just the boy baby data, and the object that gets returned from the plot command is a standard matplotlib axis object, which you could then do any kind of customization that you want to the plot. So the idea of I guess what the work that I've done and we and other pandas developers have done with plotting is to creating standard kinds of sort of line and multidimensional line and bar plots, scatter plot matrices, and those sorts of things very easy. But they return the underlying matplotlib object, so you can apply further customizations and formatting and sort of make the plot look exactly like you want. So you're not limited to what the library gives you. So you can customize basically to your heart's content. So somebody asked about, would you recommend this for huge data sets, for example, a table with 200 million rows and probably around 100 columns? Would it scale properly, or would it crash and run out of memory? I guess the question would be, it depends on the machine that you're running it on. So pandas, by and large, and this is true of much of the rest of the Python ecosystem, are tools for sort of small and medium data as opposed to big data. So you wouldn't use pandas as a replacement for, say, HBase or another sort of scalable column database. There is work being very actively done. The folks at Continuum Analytics and a number of other people are working very actively to build big data processing tools for Python. But if you've got a multi-terabyte data set, this wouldn't necessarily be the tool to reach for right now. It might be in a couple of years, but I guess we'll have to see how the software develops. It becomes quite a different problem when the data has to be spread, has to be fully out of core, and maybe have to be spread across many different machines. So somebody asked, what interface am I using to type the Python command? So this is the IPython notebook. So the IPython project is a lot more than the sort of notebook format that I showed you. This was developed within the last 2 years and has really been a huge boon for reproducible research and interactive data exploration. The IPython project itself, most people just use it as a interactive terminal, interactive shell environment for doing software development. I use it quite a lot for that, but it also has this great sort of web notebook tool. You can even run this notebook on Amazon EC2 or any cloud computing platform and sort of run your data analysis remotely instead of locally. So if you have a giant data set and your laptop only has 4 gigs of RAM and you need a high memory EC2 instance, you could fire up the notebook and do your data processing on Amazon. So another person asked that they're interested in creating a high-speed HDF5 data repository for aggregating and slicing, grouping big data. Is there any plans to support on-disk data frame slicing and indexing? It's definitely something that I'm very interested in. There are definitely some implementation challenges, but I've been talking about it for quite a long time. So if that's something that appeals to you, I would encourage you to sort of join the mailing list and sort of engage in the conversation, and particularly with helping the open source people who are heavily involved with development of pandas and other libraries understand the use cases. So another person asked, what books and web links in addition to the book, do I recommend for the non-Python user to get into Python quickly and efficiently? I guess one of the main goals of the book was for the book to be, that resource which helps folks, get up and running and productive with the tools. There's a number of other resources on the internet. So there's, you would have to Google for it, but there are SciPy lectures. If you Google for SciPy lectures, there's a compendium of tutorials for that is more focused on scientific computing, so optimization and signal processing and image processing and sort of scientific computing topics. But it's also an excellent resource and source of examples for people who are looking to learn Python. Could we integrate pandas with Orange for better visualization of data? You aren't the first person to ask about integration with Orange, which is a data mining and machine learning suite. I would be interested in that. I think if that's I don't see what would necessarily be barriers to connecting pandas to Orange or another data mining suite, but I think definitely the best thing would be someone with experience with one of those projects to get involved with the project. I would certainly be happy to have you. And let's say last question. Can you speak specifically to what Python usage you've seen for users who are currently leveraging SAS, proc, SQL? So what areas are easier to do in Python and dealing with very large SQL, Teradata, and DBs? So I see a lot of people who are using Python and pandas to do data processing, who are traditionally doing a lot of SAS or SQL and writing. I guess with standard SQL, people would write very complicated stored procedures, and now it's pretty simple to do some of this SQL-style data processing directly in Python. So that's very attractive for users to be able to have a full set of merge and join operations and data aggregation, and to be able to do more flexible data aggregation because you can apply arbitrary Python code to the groups of data rather than being limited by the set of tools that's provided in, say, SQL. I don't personally have a great deal of experience with SAS, but I know that in general there's been sort of a migration away from SAS toward R and Python and other data analysis environments. So and I guess the last question, where does the project need the most help from community members? I think definitely the best way that people can help with the project is to contribute cookbook examples. You build an analysis and you share that on the internet so that when people are learning about the tools, that they have lots of resources available to see the real world applications and how people are applying the tools to solve their problems. Definitely, the documentation. Always is sort of you can spend infinite amount of time writing documentation. Particularly, I think there are a lot of folks that use R or use other data analysis environments, and I think a great thing to have would be like a Rosetta Stone of data analysis to help people who can translate their knowledge from one place to another without having to spend a lot of time sort of reading documentation. So if you know how to use Plier in R, that you could translate your knowledge of Plier and use group by in pandas. So those kinds of things are extraordinarily useful. And you see people blogging about using Python for data analysis, and that's all been extraordinarily helpful for helping people get up and running. So that's. So yes, Mina, how are we on time? I think we're getting close to the hour.
Spot on. We are at the top of the hour. So with that, folks, we are going to say a very, very big thank you to Wes for presenting an outstanding webcast for us all. Thank you, Wes, for sharing all your knowledge and expertise, and your live demos were just so fascinating. And judging by the audience comments, they were really, really impressed and learned a lot from your presentation today. Folks that attended today's event, we thank you for attending and hope you benefited from it. We'd like to let you all know that Wes is speaking at the upcoming Strata Conference in New York. There is still time to save 20% on your tickets. Use code OLC10 when you're purchasing your tickets on strataconf.com/strata2012, October 23rd to the 25th. And if you enjoyed hearing Wes's presentation today, you might want to attend his session at the conference and go meet him and shake his hand. Also, we'd like to let you know we pushed out a code to you all. You can save a little bit of money today, pre-order Wes's book. It's going to be out here in just the next couple of days, and if you like what you heard today, wow, just imagine how much more information that book has, and it can save you so much time and give you lots of good tips in your day-to-day. So we did push out a code to you all in the group chat. Please open the group chat if you haven't done so. Look at the code. We encourage you to check out the book. Again, thank you, Wes. Thank you, everyone. This will conclude our webcast today. Goodbye, everybody.